got this PhD at ETH a couple of years ago, working, or a few years ago now, working with Sergeant Chapkun, and then went to Imperial College London for 2 years before moving very recently to CyLab, and also as an affiliate at DataSet. Arthur is probably quite famous to all of you who are doing work in cryptocurrencies because he's publishing like crazy. But he's also the person who started, I think, the first DeFi course in the whole world, right? The course that you did with Don Song and a couple of other people, which was really, really cool to the point that I stole some of their materials to put them in my course here. So with that, Arthur, the floor is yours. Sorry.
Yeah, thank you so much for the very kind introduction. Really happy to be here and to make it to the state. It's the first time for me actually at CMU and in Pennsylvania in general. So it's a really very pleasantly green place. A lot of hills to cycle around. So today I chose to enhance or modify slightly the talk. So please apologies for me taking that liberty. But I'll be still speaking about whether we need smart contract audits, as I advertised earlier. But we'll go a bit broader in the sense of how to use LLMs, also in another security-related use case. And while my full-time position is at UCL and I also work with Don at Berkeley, my real main occupation, I would say, is being a prompt engineer. So that's really my day job. So let's get started on the DeFi side. So decentralized finance is a financial ecosystem that's built on top of blockchains, meaning you can have, for example, an exchange, liquidation mechanisms, you can have lending platforms, you can have perpetuals, so different financial constructs on top of a decentralized ledger, right? That's decentralized finance. And as such, there are what's called DeFi attacks that are happening, which are essentially high-value transaction extracting value from that ecosystem. Now, we do not have any clear definition of what an attack is. There's no, as far as I'm aware, no formal definition of what is malicious and what is benign. So I will refrain from giving you any definition, but we can maybe call certain transactions abnormal or outlier-rich. So in these DeFi attacks, combined with other financial activities such as arbitrage, sandwich attacks, and liquidations, in total and roughly per year, and obviously this depends a little bit on the market cycles, they amount to roughly $1.5 billion per year that are being extracted from that ecosystem. Right? Primarily, this is on the Ethereum blockchain. This is still the most active blockchains, but other blockchains are catching up and similarly active and can find similar patterns there. So that's roughly the size. So the pace of DeFi attacks has also grown, at least in recent years. I think this year we're still up to about $700 or $800 million being lost. So you can see here the magnitude increased in recent times. And you can also see that it's actually touching on different system layers. What I mean by different system layers is, for example, a smart contract layer. So a reentrancy vulnerability, I would classify it as a smart contract layer vulnerability. But there are also protocol layer vulnerabilities. So depending on which actions you choose in a DeFi application, you can combine them in a smart way to, for example, cause an oracle manipulation and then profit through arbitrage from that manipulation. So one particularly fun, maybe malicious strategy, you could say, is the imitation. So where you imitate other people's transactions. So once you observe an incoming transaction, for example, on the P2P layer of a blockchain, well, you can replace certain data within that transaction, sign this new transaction and broadcast your copy. And ideally you do so by front running the original transaction. And that's called an imitation attack. We've presented a very simple algorithm, like a string copy replace algorithm that can do this rather easily in a few lines of code. But we have also looked into more sophisticated methods. So these are really profitable methods if you just imitate other people's transactions, and they have been shown to be real-time capable.
So I feel like I don't fully understand the attack. are you just duplicating every transaction you see, or is there some way to select the ones that are going to be profitable?
So should I repeat the question for the people in Zoom, or is that
Probably better to.
repeat?
We can hear it.
Okay,
You
cool.
can.
Okay, cool. So an imitation, or the process of an imitation, you would try to apply to every transaction you see. So whenever you see an incoming transaction, for example, you will try to replace the sender with your own address in the input data to the transaction, right? Which typically in the transaction, you call a smart contract function, and you have a certain parameter, certain input data. If there's a sender address of the original sender, you will also try to replace that, for example, with your own address. And that you will try on every transaction. Then you will first simulate locally, given your current blockchain state, will I earn money? Is that a profitable imitation? And if it is, you broadcast. If it's not, you just discard it. And that takes like on the order of a few hundred milliseconds, right? So that's why, and you can parallelize it beautifully, right? So because these transactions, they all depend on the same blockchain state. Okay, they could have some dependencies, obviously, but you assume for simplicity that that's it. And then you just try it on all.
But what about the signature? Can you just spoof the signature? How can you generate a valid signature if you change some of the fields of the transaction?
So you can only you cannot spoof a signature, right? You can only sign with your own private key. So that's at least our assumption here. And that means that if there is some kind of authorization check, for example, the original sender had access to a certain number of tokens that only this sender had access to, then your imitation would fail, right? Unless you create like your own, unless you have a more sophisticated mechanism that identifies what is required to imitate and constructs that transaction.
So in this case, if it's a single transaction, then like is it arbitrage, or is it like whether it's profitable? Does it depend on my value? Like, because if you are buying something, then whether I consider that profitable depends on my valuation of the item. So what kind of profitable are you?
Thank you for that question. You're actually alluding to how do you measure whether something is profitable or not, right? You need some kind of an oracle. In our work, at least, what we have typically done is we have a base currency, for example, the native currency of the blockchain that you take as a base currency. And whatever this transaction generates, you convert it to that base currency, right? And that requires an exchanges, it requires oracles and so on. But if that value is kind of superior to what you had before, then it's profitable.
So some level, you're stealing money, you're sort of stealing the like clever idea somebody had to create this transaction.
Absolutely, yes. Cool. Well, in some cases, we've seen that people are depositing funds or moving funds without. I mean, in some cases, there are access control issues in smart contracts. For example, modifiers missing on functions. So the imitations, you could say that they are stealing funds because you are taking funds that were not supposed to be accessible. So that's more an underlying issue then, right? Yeah. But it's in essence, you copy a strategy, you execute a strategy, and if the state or the conditions, the blockchain conditions allow you to do that, then it's an anyone can take transaction.
Which type is like more common? Is it like just exploiting the price difference, or people finding bugs in smart contracts and trying to get stuff for free?
You're asking which kinds of transactions are imitatable?
Yeah, like this copy attack when it's observed in practice, but which type is more common?
So we haven't done the thorough study on classifying these copycat transactions, but there are DeFi attacks part of it. So these are arbitrage, liquidations can be part of it. Technically, whenever there's an opportunity that anyone can take, then it's imitable. Whether your solution then is able to catch it depends on your implementation and on your design. But as long as there's no cryptographic protection against it, then it should be imitable. Right? But just to give you some numbers here, so this is what we measured. So we have a naive imitation. That's the one I mentioned earlier, where we just string replace a few things. At least according to our archive nodes, which run on historical states, you can see this generates a few million over a year. And then we have ape, which is it was you just presented at Usenix. That's a bit more sophisticated method, and it can generate or it can extract, imitate more, so to speak. Whenever you see like these big moves up, that's typically a DeFi attack that's being captured. So these are rather substantial transactions then. All right, so I guess we're clear that this space is rather hostile, so to speak, right? It's really a dark forest we're living in. I want to give you one example of an attack, how an attack was executed. So what's the kind of the pipeline? And this is in the Elastic Swap from December 2022. It's an attack that was executed on two different chains. So there was one attack first on the Avalanche blockchain. So here this is transaction 0. The green arrow here, this one indicates that this transaction succeeded. The red arrow, the red signal here signifies that this transaction failed. So it did not execute successfully. So on the Avalanche blockchain, there was a transaction 0. We labeled this as potentially an attacker, and he called the function go in a smart contract, and he extracted some monetary amount from this Elastic Swap DeFi application. Now let's look at the Ethereum version of that attack. You can see 3 transactions, right? Attacker, so transaction 1 attacker, transaction 2 white attacker, and transaction 3 white attacker. So based on the data that you're being shown here, why did the transaction 1 fail? You can kind of ignore the Avalanche one, the transaction 0 is irrelevant. So here, this is the time axis, right? So when things kind of appeared. This transaction 1 appeared on the peer-to-peer layer, and transaction 3 here also appeared on the peer-to-peer layer. The transaction 2, however, did not appear on the peer-to-peer layer. It was mined through a private channel, what's called, for example, a block relayer. So any idea why transaction 2 succeeded, but transaction 1 did not?
The second one.
Exactly. So the second transaction was mined before the first transaction, right? So it took the opportunity from the first transaction. So we as an outside observer, right, we can only see transaction 0 first appearing, then transaction 1, then there was a block mined with transaction 2, and then transaction 3 was it's appeared on the peer-to-peer layer. But so in this particular case, this transaction 2 was done by apparently some white hat hacker who was imitating this transaction 1. But now, why do we have 2 transactions from the white hat hacker? Why is there transaction 2 and transaction 3? So he tried, apparently this white hat hacker tried to go over a private network and over the P2P network. Why would he do that?
Maybe he tried to go over the peer-to-peer network first, and that failed, and he went to the blocks route. I mean, that stuff was detected, but not necessarily mined. I mean, it might have been just following the network and they realized that he had been hit on
All right.
the first one.
Yeah, that's a good comment, almost. But okay, I can add a bit more context. the time difference here, right, between the transaction 1 and transaction 3 is only 250 milliseconds. So there's not much time, right?
His transaction could still get picked up by public miners too.
Correct. Exactly. So like this white hat hacker, he went over a private network and over the public network, because not all miners do partake in this private mining network, right? So there is a chance that the next block will not be mined by a miner that's actually connected to BlockXroute in this example. So to maximize your chances of success as a front runner here, you want to go over as many chances as possible to reach as many miners as possible, and just to increase your odds of success speed. And these 250 milliseconds here, this is a rather short time frame, right? So we can really learn a few items here about this white hat hacker. So he's definitely bilingual, right? He speaks on the P2P layer and over our private relayers. He can mimic or imitate and front run in 250 milliseconds. So that's not manual work, right? That's rather fast. And he bribed the correct amount to the miners. So he bribed in total a 50% bribe, which is quite substantial, obviously, for the miners. But that's what he provided to the miners, so that the transaction gets mined. Yeah, the total amount, vulnerable amount, he was over 500 ether in this particular case. The white hat hacker returned the funds, as far as I'm aware, and got 44 ether as bounty. So it's a 10% bounty. That's a typical kind of amount.
So I'm trying to understand better the attack. So the attacker was on the blockchain and was trying to observe transactions and then mimic a transaction before that transaction was like put into a block. Correct. So that he could, or they could get the 500 Ethereum coins before that original transaction that was sent. Okay, so it's like a race condition, like whichever gets like mined first. Is that correct?
That's correct. So whenever in a blockchain, whenever you want to issue a transaction, you want to have a transaction executed, there's a lag between the moment you sign the transaction on your local machine and the time that it's included in the blockchain. And so there are different ways of including the transaction in the blockchain. You can either send it over the P2P network, which is public, to the miners, or you can send it through private channels to the miners as well. So these are the two kind of methods. And these are asynchronous networks. There's a time delay between your transaction reaching the miners as well as the next block being mined. So, and this time window, is the race condition in which different actors can try to imitate each other or try to front run.
And what was in this case? What was the transaction that basically profited 500 Ethereum coins?
There was a bug in the application of Elasticsearch which allowed you to extract that monetary amount.
So was the original transaction from an attacker too?
So here we have 4 transactions, right? So I call this an attacker because it's just the very first one, and apparently this attacker did not return any funds. I call this an attacker because it uses the same function name as on the Avalanche chain, right? But I have no ground truth, right? I don't know whether it's an attacker or I don't even know what's malicious or not, right? We don't have a definition of attack, so to speak. But I call this one a white hat hacker because he returned funds in exchange for a 10% bounty. And we can identify, well, we can assume that these two are related, and we know from a timestamp perspective that this one came after the initial transaction, which was public. Assuming our nodes have the correct timestamp, obviously it's an asynchronous network. We don't know for sure. Obviously.
Yeah, but you said that even the original transaction was trying to take advantage of a bug. So an attacker tried to imitate a transaction that was in and of itself malicious because it was trying to exploit a bug.
Correct. Right.
So it's basically hackers trying to race with each other.
Absolutely. So you have a hacker coming with an attack. Another guy, he sees the attack, he wants to counter attack with the same attack, with the same strategy. So it's an imitation. All right, so it's the Wild West, right? So how do we secure applications in this space? Well, there are 3 stages in which I feel we can introduce security mechanisms. So it's pre-deployment. Before you deploy a smart contract, you can do audits, right? You can manually audit contracts. We can also do a pre-audit. So this will be part of the talk today, where we apply large language models to audit a contract. But what can we do after deployment of a contract? Well, after the deployment, we can perform a real-time intrusion detection by, for example, imitating other people's attacks. If we imitate an attack and divert the funds to a safe address, and then we could be able to return the funds to the original project. We could try the similarity detection, where we applied similarity detection between different attacks, so that's also possible. And what can we do further? Well, after an incident, even if an incident happened, even if a protocol got hacked, we can perform a so-called post-imitation, whereby most of the times, as far as we have seen, attacks are not being executed with optimal parameters. So that means the attacker leave money on the table. Sometimes there are millions of dollars left in the smart contracts that can still be extracted. So you could technically do an imitation and change the parameters to then extract the remaining amounts in an automated process. So you see, there's a lot of defense and depth approaches that we can apply to smart contracts. It's really not only about the audit at the beginning. There are, I feel, a lot of things we can do to secure smart contracts more reliably than it's being done now. All right, so today's talk, I want to focus on the pre-audit and BlockGPT. So pre-audit is this idea of what if, it's with my amazing courses here at RDI, Imperial, and UCL. And the idea is really, what if, sorry?
I think we had one question in the chat from the previous segment.
Yeah.
It's in the chat.
Yeah, no, let me read it to you.
Oh, okay, I'll check.
Does this work if the transaction is issued using flashbots? For example, I think the question was for the first, the copy attack.
So if a transaction is being mined through private channels and you cannot observe it, then you cannot imitate it. However, if a transaction is mined, and we've seen many attacks are being executed over several attacks, then and you detect the first one, then you may be able to, for example, pause your DeFi protocol and prevent the other attacks. So it's not necessary. I mean, yes. So a privately mined transaction is so to speak safer for an attacker, definitely. And I expect that transactions will be more and more private in general in the space.
Yeah, I wanted to ask, like, do you have a sense of how many transactions are submitted through private pools like flashbots, and how many users are still just using the public pool?
So we have in our imitation paper, we have a table where we show, and I think at the time it was roughly 30% of the attacks were done through private networks. And roughly 70% were going over the peer-to-peer still.
This is for attacks, but what about normal users?
There's no study, to my understanding, that has measured that actually yet.
I think it's like 4.
I have one for flashbots. I'll put a link in the chat. It's
Okay.
pretty high.
Thank you. All right, good. So pre-audit, right? So what if we had this very simple interface where we can just paste our smart contract, and then we say, okay, thank you. In 5 minutes, you receive your audit or your pre-audit. And then you have an automated smart contract review that looks almost as similar to like a professional manual audit. That would be great, right? So the idea of this is literally we take a smart contract, we add a few definitions of attacks. For example, we take a reentrancy attack and we add the definition of what is a reentrancy. And we paste this into, for example, ChatGPT. And then ChatGPT tells us, well, this contract is vulnerable because, or no, it's not vulnerable because some other reason. And naturally, we can use a variety of reviewers here, for example, a different LLM like Claude or Llama 2 or whatever, right? So you can have a set of reviewers that are reviewing your contract, depending on the input that you get. That would be great. So we tried that. The types of vulnerabilities that we tested were derived from an SOK on DeFi attacks that we did before. So where we had 38 categories, for example, reentrancy or on-chain oracle manipulation, which are, by the way, the most common types of attacks. And we had a data set of 52 vulnerable contracts that we used to evaluate whether this could work. And what are the results? These are here the results, and you will see, well, the false positives of Claude and GPT are definitely lower than the random model, but it's still quite high. And the true positives are not much higher than the random model. So in essence, what we found is that the models, they do find vulnerabilities, but they have a very high false positive rate, which incurs a tremendous amount of costs on manually auditing then the result of the large language model. Well, we only did, this is a one-shot kind of example, right? So what we also tested then is whether we can do mutation testing. So we took a contract, which we think is super secure, we coded it ourselves. And yeah, we're very confident it's super secure. We manually added then a vulnerability and tried to ask the models about this particular contract. So in here, GPT-4 performed not too badly. And specifically GPT-4 in a non-binary setting. So non-binary means we ask it to verbosely explain why there's a vulnerability, not just a yes or no binary classifier. But I would like to add that our contracts that we created are less likely to be real world applicable because they're kind of toy examples. They're not as big and as complex as real DeFi applications. So I'm not too sure how representative that result is. Then the next thing we tried is to have a chain of thought. So a chain of thought is where you perform a first query to the model. So you perform a first query to the LLM, and then the LLM tells you something about it, and then you ask a follow-up question about it. So it's called chain of thought reasoning, which did improve our results to some degree, but not substantially. So there are a lot of limitations to this kind of work yet. So we don't have much training data, right? We just have a few kind of examples of where we know that there have been bugs and there's no complete data set. We cannot easily reproduce this kind of study because the large language models that we use, they do change frequently, right? So ideally we would use some more open source version where we have a seed that we can control. We had a lot of false positives. Sometimes we had to truncate the smart contract because it didn't fit into the context. Although I have to say we had access to the 32K model from GPT, from OpenAI, which I think 80% of the contracts actually fit into that context, which was good. And we had the 100K contexts of Claude, where, as far as I know, all the contracts actually fitted. But we didn't test much on, for example, the model temperature. So there's still a lot to be done, and we didn't fine tune either. So we're currently this is still work in progress. So we're still working on fine tuning a model that tries to identify vulnerabilities in smart contracts.
On top of training data, you mentioned there's a pool of 52 vulnerable contracts.
Yep.
Were those ones that were like publicly discussed on the internet?
That's another issue. So they were publicly discussed, and hence it could be that the models had learned about them. But if that were the case, then I would have thought that the models should have been more better. It's actually the reason why we did mutation testing, right? Because if we create the contracts ourselves and test the model on manually added vulnerabilities, then we could think that the models had not seen that data before. Yeah. Very good point. So yeah, long story short, we still do need manual audits for now, right? But there's a lot of open source data out there, right, on what is a vulnerable contract and why. So yeah, we still have hope that we can improve auditing through this process. Cool. So the second topic, and also still work in progress work, I would like to discuss today is BlockGPT with my co-authors here. So we try to apply an LLM to anomaly detection of blockchain transaction. So the typical way how an LLM is trained is here the following, and you can see there are different stages depending on which kind of model you would like to have. If you want to have just a base model, like for example GPT, you just need pre-training. So-called, this is the first step. And in the pre-training step, you only need to rely on a huge data set. You don't need to have any human contractors that create like prompt response pairs or so forth. So in our case, we actually looked at only the pre-training, but if you want to, for example, create a ChatGPT model, then you would need to go through the other steps, like you need to have the supervised fine-tuning, reward modeling, and then the RHLF step in the last part, which is definitely more involved and also requires human labor. So just to give you a bit of context, if I speak about GPT, then I really mean just this very first model, right? Like just a pre-training phase. Well, so how can we apply this kind of model to anomaly detection? Well, what we try to do is to have kind of an unsupervised or self-supervised learning for smart contract anomaly detection on transaction execution traces. So whenever you execute a transaction, you get a trace. And the trace tells you, for example, which function is called with which parameters, right? So that's the execution trace. And we had a data set of 124 attacks, and we found that this model is capable of identifying 20 of these attacks as the most abnormal transactions. And the other 20 is the second most abnormal, and 7 as first most abnormal. So yeah, we can discuss about metrics and how to kind of score an IDS. Obviously, there are various ways, but this model seems to somewhat detect some of these attacks. And I will go into more details in a bit. Just to give you also a hint on the performance. So this seems to be rather performant, at least when you batch things into the GPU. We had about 2,000 transactions per second as a throughput, which should be enough for the roughly 10 to 15 transactions that Ethereum at the moment supports. So how did we build this, or what were the assumptions? Let's start with the threat model. So we assume a computationally bounded adversary, and this adversary just wants to make money, right? That's the reward that the adversary is looking for. We have two types of adversaries that we already kind of alluded to earlier. We have one observable. So if the attack propagates on a peer-to-peer layer, everybody can observe it. And if it's hidden, well, then he is using, for example, a Flashbots relay or another front-running as a service provider. Then, well, if we would apply traditional machine learning techniques, we would need, for example, a binary classifier on some labels, right? We would need some kind of a function that tells us, given a transaction, is it benign or is it malicious? But we don't have that much data. As I mentioned earlier, for the pre-audit, we had only 52 vulnerable contract examples. Here we have 124 attacks. That's not enough for traditional machine learning methods to really be effective. So we only have about 100 attacks per year, even less, right? They are significant in size, but we don't have many data points, so to speak. So what we try to do is to build the intrusion detection based on an estimated likelihood rank. So given the DeFi application, what BlockGPT does, it estimates the log likelihood of a trace of all the transactions that are involved in this app. So I'll show this visually in the next slide. But you can think of it, we really take all transactions that interact with an application. Right? This is our corpus. And then we cut kind of like the top K, and we say these are probably the most abnormal transactions, right? We can sort them. And this K depends on how many false positives are you willing to take. And so what the costs are you willing to kind of like have when running this intrusion detection system. What I think is really cool is that we don't need any label data for this training here, because in this pre-training phase, we can just use the entire corpus. We don't have to have any labels on whether a transaction is malicious or not. We just have this concept of abnormality. So if I visualize what I just meant, you can see here in the first step, we take all the transactions that interact with an application. We pre-train the BlockGPT model with that. Then we provided a new transaction and we ask it how abnormal is that new transaction relative to the previous transaction.
Quick question. I mean, I'm sure you'll talk about false positives and all of that later, but it seems like somewhat esoteric arbitrage exploitation opportunities that could be flagged as abnormal, and that's not necessarily an attack. It's just somebody being clever.
Absolutely. Yeah. Yeah. So we are measuring abnormality. Doesn't have to be. It's not necessarily related to any monetary amount. That's an advantage, but also a disadvantage as you.
So you still need to do manual audits.
You still need to look into the false positives here. Yeah. It's kind of you can think of it as a filter, right? But any intrusion detection system will have some sort of false positives. So what are the advantages of such a system if it works to some degree? And working means it is relative, right? Depending on your requirement. Technically, you don't have any engineered rules, right? So it can adapt. So it can detect new attacks that are also not covered by existing rules or known attack patterns. But what I feel is really interesting is it can detect non-profitable transactions where an attacker is trying to, for example, execute an attack and we've seen this actually on chain. Some attackers, they try their attack without stealing much, just to try it out, and then they try the real attack. So technically, such a system should be able to detect it, because whenever you want to detect an attack, I guess the most intuitive way would be what kind of transaction makes the most money. But sometimes those are not the first signs of an attack. So which dataset did we use? Well, we used 68 million transactions from the DeFi application that we looked into. So this was over a time frame of 1,500 days. And that's the pre-training. So we used a labeled dataset only for the evaluation afterwards. And here we had 124 DeFi attacks. Sometimes an attack consists of multiple transactions. So if BlockGPT finds one of them, we consider it to be positive. That could be, there's still room for improvement, I guess, because we need to find the first attack ideally, right? The other ones are less important, but the first one should be found. So our data set of applications, they all have at least one incident, and that incident was either on a smart contract, on the protocol, or on the auxiliary layer. Also, the activity is rather diverse, between 400,000 to 600,000 transactions each. So it's a rather diverse data set. Why don't the probabilities match up here to 100%? Any idea? Exactly. Yeah. Exactly. The audits. Yeah. Some attacks are multiple layers, so it's not that. Good. So this is the architecture of BlockGPT that we try to apply here. So we have an archive node. This gives you the historical blockchain states. You can extract the trace. So we built an intermediate trace representation here. Then we apply a vocabulary, and then we use a transformer to estimate the max likelihood. For the tokenization here, you can think of it as taking the call trace, stack trace, and log trace, building a tree, and then linearizing this tree. So this is how we constructed this. It can be done differently. I think here there are different choices that you can have as a blockchain engineer to take as much data as possible. One of the problems, and I guess everybody who has used ChatGPT knows that, there's a limited context size, right? So 512 or 1,000 tokens. And we have the same issue here. So what we tried to do is to have a customized tokenization for DeFi. So we had about 100+ K tokens that we defined that are the most frequently used. So most of them were Ethereum addresses, many of them were function signatures, but we technically, if we can fit more tokens, we could fit EVM execution logs and so on. So we were not able to fit much data into the transformer because of the limits here. We applied an 8-layer transformer and we had about 1 billion parameters. So it's a rather small model if you compare it to existing models such as ChatGPT. So what are the results? Well, we found that attacks are ranked as most abnormal are the following here. So these are actual attacks that we found. Right? But yeah, I can give you the false positives numbers also as you asked earlier. I have them in the back slides actually. So here. So let's see it. Again. Oh, sharing screen. Stop. Okay.
Sam has a question.
Okay.
Go ahead.
Great. Oh, we can go into the question. Where's the question?
Sam.
Yeah, I had a question, which was just, Arthur, did you build your own tokenizer completely for this?
Yes. Yes.
Okay, yeah, I'd be very interested to hear about that at some point.
Okay, cool. Yeah. I mean, it's as far as I understand, this was required. Otherwise, we couldn't have added it. Yeah. So regarding the false positive rates, so here you can see we have two metrics. One which is the absolute ranking alarm threshold, right? So top 1, top 2, top 3, and one is the percentage rating alarm threshold. So, and you can also see there are different sizes of number of transactions that the network is that the application is having. So for example, if you have a DeFi application with 10,000 transactions, which represents roughly 25% of our data set, then we have an average false positive rate of 0.08%. But this is rather small because we are considering the top 3, right? So top 3 relative to 10,000 is rather small. So naturally, if you have a transaction, if you have a DeFi application with less than 100 transactions, then the top 3 will consist of a lot of false positives, right? Because you're considering the top 3 as the most abnormal, right? So yeah, I'm not too sure whether this number is too representative because it literally depends on the input size, right? On the number of transactions that are applying with the number of transactions that the DeFi application has experienced so far. So I feel currently the most telling metric is that BlockGPT can find or ranks 20 of the 124 attacks as the most abnormal transactions. So we have 68 million transactions in total, 124 are attacks, and 20 are being ranked as the most abnormal out of these 68 million. So I feel that's a quite good indicator that BlockGPT is able to identify attacks. Okay. So I just wanted to position BlockGPT a bit also in the related work landscape. So we have rank-based. So this is a rank-based approach, right? Your assumed prior knowledge is just all the transactions. You don't need any labels. You don't need any source code. And it's real-time capable, but you will have this notion of false positives that is a certain cost that you have. You can have reward-based mechanisms to detect attacks, right? Like an imitation tool is actually can be used as an intrusion detection system. And you can apply pattern matching. You can apply proof-based tools. So these are roughly like the variety of tools that we see that could be used as an intrusion detection system in the field. So yeah, to conclude, we have the first unsupervised learning. for smart contract anomaly detection. It does identify, I'd say, it proportionally identifies 20 out of 68 million transactions as the most abnormal, which is a promising sign. I'm still not sure yet of whether this is practical in the real world, because you will have a certain set of false positives that you need to look into manually in real time, right? So you need to have a intrusion detection team that is behind this kind of tool. But we can effectively detect attacks without engineered rules, right? So you do not need to invest into a team that keeps your ideas up to date, so to speak. Also, the throughput seems to be promising. So we have a high throughput, and I think I'm confident, at least on the performance, that it should be good enough for the current mainstream blockchains. Cool, thank you. Yeah, this was.
Hey, great talk. So I have kind of maybe a bit of a wacky question here, but if you combine the two approaches, so if you could have a semantic embedding of smart contracts, you could potentially simulate real user and potentially real attack behavior on smart contracts that are not yet deployed ahead of time before deployment to potentially simulate types of attacks that you might observe. What do you think about that?
So you mean to create, so you have a smart contract without any usage yet, right?
Without any usage yet, but you have a semantic embedding of it. So you have like a corpus, like for SmartGPT of smart contracts and transaction traces and anomalous transactions and things like that.
But how do you make sure that the transactions are representative of user behavior or of attacks in that case, right? Because you need this kind of generator, right? That is.
So you have a mapping, because you have the semantic embedding of the contract. You have a mapping of that to the 68 million transactions, and so you are simulating essentially the types of transactions that you might see. Now, of course, it's going to require some more than that. This is
this is a very good point, right? I feel, and that's just a feeling, and any scientific backing yet, but I feel this kind of GPT model could be used to generate transactions, and typically where this is then being used is in the fuzzing world, where you try to fuzz a contract.
Yeah.
So, because what we could technically do is, if we know the model here tells us what's the most unlikely transaction that exists, right? Out of the, maybe we can create unlikely transactions and then use them as a. It's similar to mutation testing, just a bit more advanced, because you don't just flip bits, but you actually use a learned model that understands a bit of the semantics of the DeFi landscape.
Yeah.
Cool.
Thanks for the talk. So in the first part of the talk, you basically gave the entire source code for the contract to an LLM and asked if there was a bug, right?
Yeah.
Do you think that there's, like in your experience, do you think an LLM would be better suited for like a smaller task, maybe just identifying like some invariants or something that you could then use some other methods to do bug finding with, rather than just asking it to solve the entire problem?
Yeah, it's a good question. I mean, instead of providing the entire context, you could also say, what about this function, right? You could go on the function level, but by invariant, like what specifically do you mean? Like, are you looking for like access control issues, or?
You could imagine like basically something that allow you like do like property-based testing or something, where you could maybe use some other form of methods, basically test if a property could be violated, maybe, but maybe the developers didn't write all the invariants in, and you could see how long to find them. And I'm not. I'm just kind of throwing an idea out there. I was more generally interested in like, is there a smaller problem that you think it would be better at, or is it not really clear at all?
Right. So I think what's related is the generation of specifications. No, the LLM could actually help you to generate specifications, or in a more naive way, you could ask the LLM to do the comments in the code to match the implementation. So definitely, I think these models can be helpful. Still, the accuracy is not always that high, and they sound plausible, but are not necessarily very precise.
Questions online, maybe? Or there's just Sam online. Yeah. Okay. There was something in the chat. Oh, that's
Yeah,
all.
yeah, I'm looking. There was only one question.
I had a question, but I was listening to the answer of the other question. And I forgot it.
Oh, no worries. You can feel free to shoot me an email later also, no, if you want. Yeah.
Yeah. Okay. That'd be great.
Yeah. Question?
Oh, I guess okay. So it kind of, I mean, it's more of a broader question, but did you, as part of the work, did you kind of establish what the naive, unsupervised approach would be without using like a transformer, and then compare it against that?
Yeah, that's a great question. So you could argue maybe a transformer is an overkill. I mean, there are. I think, I mean, you could use things such as BERT, I guess too, right? I mean, GPT is maybe an overkill. You could use things like BERT, I think. But otherwise, regarding anomaly detection, if you just want to have like engineered rules, there are a lot of rules that you could come up with, right? But they need to be maintained manually. So in an automated way, I'm not too certain to see other types of solutions, but they may obviously, right? There may obviously be more easier solutions.
Okay. Yeah, I was kind of thinking just in general, there's some clustering methods, right, that would look at the transactions and say, here's a few clusters. These clusters are, very dissimilar from these other ones.
Perfect. Yes. So clustering always requires a similarity metric, right? So kind of a distance function that you can come up with, and I'm not too sure whether cluster, like, okay, I mean, you need it to be real-time capable, right? You want to cluster a transaction as quickly as possible. So if you need the pairwise similarity among your set of whatever 10,000 other transactions, you need to make sure that you can compute this quick enough, right, in real time.
Yeah. I was thinking, you could maybe try something like min hash. I don't know. I was just wondering if you had looked into a naive, kind of similarity measurement. What would be a naive similarity measurement for the problem?
So actually, sorry, I have a backslide which could help here. So can you still see my screen?
Yes.
So here we try to do bytecode similarity analysis so we take the bytecode of a smart contract, we chop it into n-grams, then we create embeddings, and given the embeddings, we compute similarity among the bytecodes. And what we
got it. Okay.
For victim contracts, we found that there's actually 100% similarity among 38 out of 124 victim contracts. And if we relax the similarity to 80%, they're even more similar. And that the same reasoning applies to attacker contracts. Maybe that's something that you would say is more naive, I guess. I mean, because yeah.
Yeah, I would agree.
So that's it's not a large language model, but it's more like a simpler AI technique, so to speak.
Yeah, it'd be interesting to use your tokenizer there too.
Yeah, thank you.
All right. Let's thank Arthur. Really nice. Thank you so much.